if you have a what we call a single time constant circuit, then that means where you can collapse all the resistances and capacitances into a single resistance and a single capacitance by you know, combining the parallel and series values, and sometimes, often, what also is part of that process is that you may find that there's one capacitor or one resistor that particularly dominates. Is there a question? Okay, I didn't hear anything, so I'll take that as no. But if you do have a question, you can interrupt or you can type it in the chat. I've got it up, so if I remember it. So you might have one very large capacitance in a circuit, which is far more important than a bunch of other small capacitances, and that causes it to basically become like a single time constant circuit, at least in the most important frequencies. And if we have a low pass circuit, filter, I should say, it has this characteristic that looks like this. And as you go up in frequency, the gain will start to fall at a value of 20 dB per decade. And if you have a high pass circuit, below a certain frequency, the gain will increase at 20 dB per decade. And between those two certain frequencies, gain will be constant. So it will not be a function of frequency in this range. Gain is a function of frequency above this range, above whatever point we call it, where it starts to decrease with frequency. And gain is constant all the way down to this low end, but in between it's constant. It does not vary with frequency. And that's very useful, because that's where we want our circuits and our amplifiers to operate. I brought the wrong glasses today, so I'm going to have to hold everything really close so I can see anything. We call these frequencies where it curves down, and usually we usually call this the minus 3 dB frequency for a variety of reasons. That works out to be a good point. So usually this corner where it falls is 3 dB below this mid-band gain. Excuse me? So we call these frequencies omega 2 and omega 1 pole frequencies. They're corner frequencies, and they're also pole frequencies. And when we get into frequency response, which for the most part won't be until electronics 2, that's going to make a lot more sense. The bandwidth is the difference between these two frequencies. As I mentioned, it rushed before. If this frequency is 100 and this is 1 megahertz, then 1 megahertz minus 100 hertz is still 1 megahertz, right? And so often we just call the bandwidth to be at upper frequency. If this is 100 megahertz, then we just say the bandwidth is 100 megahertz. We know it. We don't have to subtract 100 hertz from it. And often we completely ignore this. It may not really exist, or we just ignore it often. And often, as a result, we have a response that looks more like that. That might be often what we're actually looking at, with that being a flat line. And we usually think of the transfer function. If we're looking at some T of S, is we think of it in terms of S, the complex frequency variable, and then we have the impedance, for instance, of a capacitor is 1 over SC. That'll just make things a lot easier and works out. And I'll just remind you that a low pass filter looks like this. And a high pass filter looks like that. We've got values of R and C. And when it's confusing to you to remember what's what, just remember at low frequency, at DC, nothing gets through the capacitor, right? So at low frequency, a capacitor is like an open. If this capacitor is an open, then at low frequency, we've got this circuit, right? It's an open, and that means nothing gets through. But at high frequency, it's like a short. High frequencies, it's like a short, and everything gets through. So this is high pass. And we can do the same thing at low frequencies. Well, yeah, I'll do that. Well, I'll do high frequency first. At high frequency, the capacitor is a short, and the output is 0, right? Because it's a short on the output. And at low frequencies, it's an open, and so everything gets through here. Exactly whatever voltage we have here is seen on the output here at low frequencies, and so we have a low pass. It can be really kind of confusing to remember what's what and keep that straight. And the whole key to me to do that is to work with the capacitor, and knowing that the capacitor is like a open at low frequencies. DC doesn't go through a capacitor, and it's like a short at high frequencies. And a high pass filter means that response is like that as we go up in frequency, and a low pass response is like this.